Okay, so the short lesson for today is going to be about mean or expected value of probability distributions. Now go ahead and get this copy down for yourself. And we need to understand that expected value basically is the mean. It's the average of that distribution, but it's not calculated the way a normal mean would be, because you can't just add all the outcomes up and then divide by however many there are, okay? Because they don't have equal probability or weight. Okay, another name that you might see for expected value is called a weighted average. Okay, and that basically just means that different outcomes have different probabilities or weights, and you have to take that into account when you find the average. Okay, so we're going to start by doing an example of the expected value of our dice. Okay, the one that we did on Monday. So for our dice for Monday, what I'm talking about is the sum when we're rolling 2 dice, okay? And our table, remember, okay, was from 2 to 12 and had all the different fractions. Okay, the actual formula for expected value is to take each outcome and multiply its probability, and you keep doing that until you go through all your probabilities. Okay, and the actual formula, and it's a symbol you've probably seen before. If it's not, that's a uppercase sigma, and basically what it means is a sum. Okay, and it's literally the sum of all of the outcomes times each probability, and then you add them all together. Okay, so with our dice, again, that we did on Monday, and let me see if I can get this to actually fit, and you'll probably have a better chance getting it to fit on your paper. Okay, so our first outcome was 2, and it had a 1 in 36 chance of happening. And then 3, and that was, I'm just going to go ahead and put the not reduced fractions just so that I keep track of them. Plus 3 times 2 out of 36, plus 4 times 3 out of 36, plus 5 times 4 out of 36, plus 6 times 5 out of 36. It's a big thing to put in your calculator, but the graphing calculators will do it, and they will do the stacked fractions, so it's not a big deal. And you're just going to keep adding each of your multiplied pairs. I'm not going to be able to fit it in one row. Okay, plus 10 times 3 out of 36, plus 11 times 2, plus 12 times 1. Okay, and if you multiply all those out, all the pairs, and add them together, you can prove it to yourself in your calculator, what you're going to get is 7. Okay, and so that means that's another reason why when people play craps, that 7 is both the best and the worst number. It's best if you can roll it the first time. It's the worst if you roll it any time after that, because then you lose, right, if you roll a 7. So your average, basically what this means is that in the long run, okay, and when we say the long run, we're talking about rolling 2 dice, thousands and thousands and thousands of times. The average, okay, sum of 2 dice equals 7. Okay, so in the long run, if you keep, rolling and rolling and rolling the dice, and you add up all your sums that you get, you're going to get an average of 7. Okay, now specifically in the long run is a very specific way that we phrase things in statistics, and for those of you who will be taking the class next year, we talk about what's called the law of large numbers, and that's what that means, is that in the long run, okay, not in the short term, like you can't roll 2 dice like 7 times, or 10 times or whatever and expect to get an average of 7. But if you do it like thousands and thousands of times, that's what's going to happen. Okay, and that's what expected value or mean is in this case. So another example for determining expected value, and this is one that I always like to use with my students because y'all are going to be 18 next year, and that means that you're legally able to play the lottery. So I want you to see what the actual expected value for you playing the lottery would be. Okay, so in order to do this, we need to be able to write the probability distribution. Okay, so you pay $1. That's one outcome, is that basically you just lose $1 because you're not going to win anything, right? And if you pay that dollar, these are your outcomes, right? So you're going to pay that dollar and you're going to win nothing. And the chances of losing, right? If you have a 1 in 17 million chance of winning, then you have a 16,999,999 out of 17 million chance of losing, right? If only one person, now granted I know with the tickets you can have more than one person win because they can guess the same numbers, but to make this our probability distribution, we're going to just say that that's the chances of a person losing. Okay? And again, the lowest amount that the lottery can go for the Mega Millions is 12 million. So if you win, now technically you've already spent that dollar, so what you would win would be everything but that dollar back, right? Because you don't actually, get to count that dollar you spent. And the chances of winning that, as I stated, are 1 in 17 million. And your calculator will do this as well. And it's literally, each outcome times its probability. So that would be -1 times the 16,999,999 over 17 million. Okay, plus you're going to make 11,999,000 if you win. That's just the lowest jackpot. And you have a 1 out of 17 million chance of winning. Okay, and go ahead and I'll give you a couple of minutes to put that in the calculator. And we'll talk about what you'll get. Okay, so if you've got that in your calculator, and you should have gotten an answer of -0.29. Okay, so remember, this is in the long run, right? So in the long run, so if you keep buying, one ticket every week or, whatever you want to call it, so in the long run, okay, so in the long run, you can expect, and since that's a negative, we're going to say you're losing money, to lose 29 cents every time you buy a lottery ticket. Okay, because that's your expected average. That -29 cents represents what you can basically win, in this case it's lose, every time you buy a ticket. Okay, that your average, let's say, again, that you buy a ticket every week for like, I don't know, 10 years. Okay, that's 520 tickets, right? And in the long run, you'll have spent $520, because it's $520, a dollar for a ticket. But for every 500, every dollar that you play, you can expect to lose another 29 cents. Okay, or that rather, you can expect to lose 29 cents of that dollar. Okay, so again, just to give you a short picture, 10 years, once a week, right? You've spent $520 buying the lottery tickets. And if you're expected to lose 29 cents for every dollar that you spend, okay, you would do 520, all right, times 0.29. What you can expect to basically lose out of that money, okay, is $150.80. So what you'll get back, in the long run, just, winning little bits at a time, would be 520 minus 150.80. In the long run, you'll still be out $150 of that 520 that you spent without winning anything else. So this is what you would actually have if you bought, a ticket once a week for 10 years. You would expect to basically lose $150 out of the 520 that you spent. This might be what you would get back, winning, a dollar or $2 here and there. So that's how expected value works. You're literally just multiplying each outcome times its probability. I'm going to do one more just to make sure. Okay, we're going to find the average number of people in a household. Okay, and so we have all the outcomes, 1 through 7, and we have the probabilities of getting those outcomes. So we're going to set it up and we're going to multiply. And we're going to find the average number of people living in households. Now, I don't know if people say it anymore. When I was growing up, people used to say that families had on average 1.7 kids. That's where numbers like this come from. Those averages don't necessarily represent a real amount of people. They just can't. So, that's what, I don't know, like I said, I don't know if people still say that, but, we'll find the average number of people in a household, and it's not going to be a whole number, it just isn't. So you multiply all your pairs out. I'll give you a minute to put that in your calculator. Okay, what I came up with was 2.6, and hopefully I haven't messed that up too badly. It's 2.6 people on average. Okay, now that seems kind of small, I guess, being that the distribution goes all the way up to 7, but if you were to graph this distribution, like what we talked about on Monday, based on the percentages and stuff, if you were to graph it, you would see, let's see, we need to go, okay, so that's 5, 10, 15, 20, 25, 30. So 0.3, 0.2, 0.1. Okay, so if we were to graph this, just based on, the data that we have here, and this might be something that you've seen before and discussed before as far as a description of the data, which is something that we're going to be getting into in the probability and stats unit. 7 would be about right here, and then 3, and then 1. Okay, this data is not symmetric, it's called skewed. Okay, and in this case, specifically, it is skewed to the right, and I know that seems really weird because, well, it's heavier on the left. We call this the tail, and when data is skewed like this, we say that it follows the tail, that the skew direction is whichever the direction the tail is in. Okay, but that 2.6 does sit up here because most of your data is concentrated on the left hand, on the lower numbers. Okay, so the mean would be somewhere up here. Okay, that makes sense because the mean, even with it skewed, is usually somewhere close to 50% of the data, the median or the mean. So close to 50%. Well, if this is 25 and this is 32, then this is already more than 50% of your data just here. Okay, so it makes sense that your average would be something closer to the small numbers rather than to the large numbers. Okay, so your assignment is in Canvas. It is called Expected Value, and try and have a good day. And tomorrow, if you want to, do a Google search on what we're going to be doing tomorrow, we're going to start talking about what we call binomial random variables. Okay, and the only difference between what we've been doing and a binomial is that now we're looking at only two possible outcomes, success or failure. So Lisa, what you were talking about before as far as understanding probability, remember that probability is the ways to win out of your total. So now all we care about is whether we win or lose, and those are the only two outcomes we want. So if you want to do a Google search for that and take a look at what we're going to be doing tomorrow. Like I said, it's in Canvas. It is called Expected Value. And I hope you have a wonderful rest of your day.